So in the last lecture, we talked about this problem. Okay, and we actually introduced the concept called amplification factor. Okay, and this is actually coming from the following. We actually estimate the difference between the hn plus 1, if you recall, equals to ahn, okay, versus hn plus 1 as a function of htn. Okay, so the amplifications factor are actually a linear factor that allow us to map from time step n to time step n plus 1. Okay, and this take a particular form. A equals to 1 minus lambda delta t 1 minus beta divided by 1 plus delta lambda delta t. Okay, we also talk about the stability of this algorithm. Now notice that when we have the previous step given hm and we actually try to compute hm plus 1, what we actually need to do is just to multiply this factor a, right? Okay, so a very important thing is that if I want to get hn plus 2 as a function of hn, then I will apply 2a, right? And then if I actually want to do it for another time step, then I just add another a there. Okay? Does that make sense? Okay, just one step. I'm matching it from time to time. So given one time step, let me write it down. So this is actually equal to ahn plus 1, which is equal to an plus 2. And an plus 2 is just ahn plus 2 is just equal to hn plus 3. So it's matching it using the a as the factor that allow us to mapping to the next time step. Okay, so far so good. Now the question is that if I actually wait for infinite amount of time step, what would happen? Okay, so now it really depends on what is a. So if a is greater than 1, okay, after infinite amount of time, so it goes to infinite, right? Okay, so now does it related to a steady state algorithm? Steady state phenomena? It won't, because we know that if we preserve a system that actually obey a transient diffusion problem, eventually nothing will change. It will reach eventually it will lead to the steady state solution again. So this is actually unstable. Okay. And in the last lecture, we talked about under what circumstance is actually making it stable, and that would be obviously a that are actually smaller. The absolute value of a is actually bounded by 1, right? If the factor is smaller than 1, and then you times it infinite amount of time, eventually it would actually lead to 0, okay? Okay, you just have a different decreasing rate, but it will happen. Now, if you actually look into the deviations, I don't want to repeat the algebra there. What happened is that we have we have a beta that are actually smaller or equal to 1. In this case, then that implies delta t has to be smaller than 2 divided by lambda 1 minus 2 beta. Okay? So beta greater than 1/2 is stable. Okay, beta smaller than 1/2. In this case, delta t must be smaller than this value in order to be conditionally stable. And when we say conditionally stable, this is actually the conditions. Okay, so what they translate to is that if you set beta equals to 1/2 or even equal to 0, And if your delta t is actually larger than this value, then you can see the numerical solution actually blow up. Okay, does that make sense? Okay, so far so good. Okay, so this is the review. Now I want to complete this because I want to talk about the accuracy, okay, of the algorithm. So now we know that we have the h equal to, the analytical solution actually looks like this. H equals to a e minus lambda t. Okay, that would be the analytical solutions. Okay, and the analytical A, which is actually the amplification factor that are coming from analytical solutions, not the finite difference first order Euler's rule, is actually E minus T H T. Okay. Basically just a derivative of it. Okay. Now, the important thing is that we want to actually measure how accurate our algorithm is, okay? In particular, for the three different algorithms, the forward Euler, the backward Euler, and the Craig-Nicholson. Okay, so what we actually need to do next is to compare the amplification vector, amplification factor A that are coming from the finite difference versus the A that are from here. Okay, we want to compare it, and from that we can measure the error. Okay. So far so good. Okay, so how do we do that? So amplifications vector 1. Okay, amplification factor 1 is just what we have before. Okay, and the amplifications factor 2 that we actually want to talk about is this one. Okay, what is the issue of this? So if I want to compare how accurate this is, we know this is actually the true answer. This is the approximate answer, approximations. So if we actually want to know, if we want to measure how accurate it is, what should we do? We just have one divided by the other, right? Okay, just measure the difference. Now, if I'm directly doing it, then what solution do I get? It's not very convenient, isn't it? So how do I compare the exponential expressions with equations that look like this? Okay, it's not very convenient. However, if we recall that, if we recall it from the algebra course, there's also another possibility to express the exponential operator in a series, and that is actually simply the expansions of that. And what would that look like is the following. We know that E minus delta t, E minus lambda delta t is actually equals to 1 minus lambda delta t plus 1/2 lambda delta t squared plus 1 divided by 3 quotation mark lambda delta t cubic plus, what is the next time? 1 below by 4, and then do I need to add the quotation mark? Yes. Lambda minus delta t plus etc. 4 times etc. Okay, so what is that quotation mark? Okay, so yes, exactly. So A quotation mark equals to A times a minus 1 times a minus 2 all the way over 2 until you actually times 1. Okay? Like, okay? So now, if I substitute this into these expressions, then what I would have is the following. Okay, I would have, what would I have? So the strategy is the following. Okay, so you see this is actually expressions with that doesn't quite directly compare to this, but we can actually take out the term one by one and see under what case I cannot get a zero term. Okay, does that make sense? So if I have this A, this is equation 1, this is equation 2, 1 minus 2 will give us the following expression that will give us the Euler. And that Euler would be, okay, so how do I actually take out the first term from here? If I want to get 1 here, I can simply do the following. I can add this delta, sorry. If I want to add this term, I just need to add the delta t here minus delta t. Okay, does that make sense? That I add and minus the same amount, it will be as if I did nothing, right? Okay, now I take this term here. Okay, I factor it out, so what would I get? I will get the 1 that I need, right? Okay, so now I get this 1, and then 1 minus 1 is 0, so the first order term is 0. Okay, does that make sense? Okay, did you follow? Okay, so let me write it one more time. So I want to actually expressing the first expressions like the second one. Okay, and then at some point in a high order term, I just want to give up, but I want to see how many terms I can cancel out in a polynomial setting. Okay, so I first have that term. And then what I actually want to do is that in order to take the 1 out, I need the plus lambda delta t, right? You see what I mean? Because this whole thing is divided by 1 plus lambda delta t. Okay, in order to do that, I simply do something very simple. Plus delta lambda t minus delta lambda t. Minus lambda delta t. So I did not change the values, right? Now, if I did that, then I can take out the 1 by actually taking out these 2 terms. Then what I would have remained is, what do I actually get? That would be 1 plus delta lambda delta t plus these 2 terms combined, right? Sorry. These 2 terms combined, right? So what would that be? Okay. So that would give us that would give us the beta lambda delta t. Is it correct? Because there's a 2 minor here. Okay, and then what else? Yeah, and then of course you have the minor 2. Is it correct? Do you see that? Okay. So this is a minor term, this is a minor term, so I get this plus term here, okay? And then what I have is that 1 term and this term, so 1, so that would be minus 2. Yeah, did I make a mistake? I don't think so. Okay. Okay, so and here and in the equation 2, I forgot to mention one important step. Okay, we would actually need to do is the following. we need to put A equals to E delta Tn plus H Tn. And if we work out the algebra on the E minus delta T, substitute it back to the analytical A factor, then what we will get is the following. We will get A equals to 1 minus delta T plus beta lambda delta T square plus beta square lambda beta T cubic blah, blah, blah. Okay, so I won't repeat the entire algebra, but what we will get at the end is the following. We will have the Euler that are actually equals to 1/2 minus beta times lambda delta T square plus minus 1/6 plus beta square plus lambda delta T cubic plus okay. So if we work out the algebra, this is actually what we get. Okay, so why do we care about this? Is that this gives us something called the order of accuracy. Okay, so what it actually means is the following. So the Euler can be written, what we actually interest is that we use this O term. So in general, so you can write it like this. So this is actually the first order. So this is actually meaning that only the this meaning that I can even cancel out the first term, or I can actually do it like this, 2, 3, 4. And what it means is that when I actually expand the extension as a polynomial, how many order of term can I cancel out? The higher, the more accurate. Does that make sense? Okay, like if I want to describe a polynomial, okay, and then a1 plus ax plus bx squared, if I can cancel the 2 term, I will call it first order accurate. If I can cancel all 3 terms, I will call it second order, etc., etc. Now here, if I want to increase the accuracy, so what I should do? I can simply set beta equals to 1/2, right? Okay, it will cancel out the 2 term, and I will have the higher order term. In fact, if we did it, then this term vanishes, and the term that vanishes is exactly the order of the accuracy. So if beta equals to 0, we will call it second order. Accurate. If beta is not equal to 0, beta is not equal to 1/2, then this term is not equal to 0. Okay, so what it means is that the Euler would be a function of the delta t as well. So it will be the delta t squared as well. So this is actually just first order accurate. Okay. So let me ask you the questions. Do you want first order accurate, or do you want second order accurate? You always want second order, right? Do you? Okay, but why? In that case, why you use the first order? In this case, of course, in terms of accuracy, I will always want it to be the most accurate one. I will always pick the most accurate one, right? Okay, so what cause? Okay, so do you always use second order accurate in this case? Or maybe you can actually ask the similar questions. If I want, I can introduce more term and then cancel even higher order. Okay, then I can have arbitrary order of accuracy. But do I actually impact this? What are the order that I use? Okay, so that brings up another consideration, which is actually the oscillations. Okay, so why would there be oscillations? Okay, so let's consider the the numerical oscillation that could sometimes happen, consider this fact, this operator that I map it from the n time step to the n plus 1, okay? Consider this, and then A is actually this A is actually could be written like this. Now, let's look at the psi of A, okay? Okay, so if we look at the equations, how do I actually change the psi of A? Okay, let's look at the one at the top, okay? Let's assuming that, so let's look at this term, okay? 1, of course, is greater than 0, and we assume lambda is greater than 0, and delta t is greater than 0 because you're marching in time, and beta are all greater than 0, right? Okay, you see what I mean? So now, we want to check under what beta would A become smaller than 0, okay? Now in this case, then what we actually need to consider is just this term. Okay? Now if I actually take it out, then I have this 1 minus the beta lambda delta t. So that means if beta equals to 1, lambda is always greater than 0. Okay? Does that make sense? Okay, if beta equals to 1, alpha A would always be greater than 0. Does that make sense? Right? Because if this is the case, then the right hand side is 0. So 0, of course, is always smaller than 1, right? Now consider the other case. Okay, so if beta is less than 0, if beta is less than 1, then what will happen? If it's less than 1, okay. Let's put the number, let's say 0.5, okay? So I will have 1/2 lambda delta t, okay? So does it greater or smaller than 0? It depends, right? Okay, it could be greater or smaller than 0. In fact, if A is smaller than 0, what is AA? So 2 negative will still be positive, right? Now I times another A, is it positive or negative? It will be negative again. If I times another A, it becomes positive. Okay, so what did actually happen is that just because of the numerics, I will have a zigzag pattern that look like this. Okay, and this is actually not physical. It just depends on because of the numerics, and this is actually called the seesaw oscillations, or sometimes just called oscillations in time. Okay, just because of the time algorithm. Okay, so now in summary, I have 2 choices. Beta equals to 1/2, and that one would be second order accurate, but with oscillate, but could actually oscillate. Okay, so this is one choice. Okay, I want it to be more accurate, but then numerically, the numerical algorithm may suffer from some oscillations. Okay, that's the price you pay for being more accurate. Or I can have a beta equals to 1, then I'll have first order accuracy, but no oscillations. Okay, so that would be good, right? Or I can pick anything beta that are actually smaller or equals to 1/2, and then I will have the first order accuracy, and it would oscillate. Okay. Okay. So basically, all three choices are feasible, but then they have pros and cons. Okay, like anything in life. If you want it to be more accurate, you pick the second order, but your numerical solution could oscillate because your amplification factor could be smaller than 1. Okay, could be in the negative side. If you have beta equals to 1, you don't have an oscillate solutions due to numerics, but it will only be first order accurate. If you use the forward Euler or explicit scheme, or you use anything that have beta smaller than 1, it would be first order accuracy, only first order accurate, it would oscillate, and it's only conditionally stable. Okay, so it would look like beta smaller than 1/2 is actually a bad choice, right? It has all the bad thing and none of the good thing. However, if beta equal to 0, okay, then you have one benefit, you still have all the bad thing, right? But what is the benefit of beta equal to 0? It's explicit. And if you formulate correctly, it could be matrix free. Okay, you can get rid of using the matrix to update the system. You don't have to solve a system of equations, and that could be a benefit. So it's like a different choice that you would like to make. None of them is perfect. And there are actually new efforts to derive new new time matching algorithm, like a space-time discretization, or actually other technique to actually achieve a better result. But the most basic result that you can really get is these 3 different methods. Okay. In fact, you can consider them as one family of the method in the Euler family. Okay, so I want to ask you, which one would you choose if you have to implement the code? If you want to solve a diffusion problem in probe mechanics. Huh? I will use the backward Euler. Yeah, me too. I would use the backward Euler simply because if you actually reduce the delta T, you can control the it's less accurate, okay? But then you won't have an oscillation that read the solutions. Now, but that's a personal preference, okay? I mean, I don't think that this is a right or wrong answer, and it really depends on what you want to achieve, okay? So, okay, let's take a break right now. It's a short break, and then we switch to the computer, to the Phoenix tutorial. Okay, let's take a 10 minutes break.